In this section, we'll begin to review some of the key binding interactions that drugs can use when binding to their intended target. So in this section, we will look specifically at electrostatic interactions, which is where we have interactions between groups which have opposite charges, and we'll look at hydrogen bonding as well, which occurs between a hydrogen bond donor and a hydrogen bond acceptor. So first we'll begin by looking at electrostatic interactions. So these are interactions between groups that contain opposite charges. So this can be thought of as an ionic interaction. It occurs between groups which have opposite charges. So if we have a look at the diagram, you can see here we have a negatively charged oxygen interacting with a positively charged amine. Now we can also have positively charged amine interacting with a negatively charged oxygen. So it doesn't matter which functional group, the one on the drug or the one on the target, contains this charge. Now hydrogen bonding and electrostatic interactions are the most important types of interactions for drug-target interactions. Now the strength of the interaction is inversely proportional to the distance between the partners. So the closer the two partners are, the stronger the interaction. And this type of interaction is heavily dependent on both pH and the concentration of salts. So salts such as sodium chloride can actually also interact in an ionic way. And if we take, for example, the negatively charged oxygen on this molecule, if we had a solution rich in positively charged sodium, the sodium could interact with this oxygen instead of the amine. So typically if we increase the concentration of salt within an environment, we'll weaken these electrostatic interactions. Now these interactions are also dependent on pH. So this functional group here is actually a carboxylic acid. Now it's a carboxylic acid that has lost its proton. So the proton or the hydrogen that would normally sit on this oxygen and neutralize the negative charge. So again, if we have an environment that contains a lot of acid, it means there's a lot of positively charged hydrogens floating around in the solution. We could end up replacing the hydrogen on this group and preventing it from having a negative charge. So pH and salt concentration can drastically affect the strength of ionic interactions. Now, for an ionic interaction, a hydrophobic environment is often more favourable. So this means an environment that is less tolerant of water than an environment that likes water more. So environments that are less polar can better support electrostatic interactions. Now the reason for this is that water can also bind to charged species. And so in this example down here, we could get a water molecule that, for example, that binds to this amino group. Now when it does that, it could physically block the drug molecule from coming in and having that interaction. So having an electrostatic interaction within an environment that contains low water or is free from water is more favourable than having an electrostatic interaction in an environment with lots of water. Now proteins contain some regions that are really water loving, so really hydrophilic. They're really polar, they support lots of water molecules, and others have environments, and other regions may be an environment where water isn't tolerated as much, so it could be a hydrophobic environment. And electrostatic interactions are most favourable within those hydrophobic environments, so they prevent water from getting in the way and preventing binding. Now, the relationship between the strength of the interaction and the distance of the interaction is less important for electrostatic interactions than for other types of bonding. And we'll see a bit more about that later on. But an electrostatic interaction is the strongest type of interaction that you can get as an intermolecular bonding interaction. So electrostatic interactions are very, very strong. Now what this means is they're felt over a very long distance in comparison to things like hydrogen bonding or dipole-dipole interactions that we'll see later on. So electrostatic interactions are felt over the longest distance, and this means that this type of interaction is very important for providing the initial attraction between a drug molecule and its intended target. If we put on groups capable of having electrostatic interactions, we can increase the likelihood that the drug will reach its intended target. Now, the bond strength for an electrostatic interaction is very, very high. So this can range from 20 to 40 kilojoules per mole. Now, you don't need to worry about the number particularly, but what you do need to know is that an electrostatic interaction is incredibly strong. And so it is used not only to provide a very strong interaction within the binding site to hold the drug molecule in place, but it's also used to initially attract the drug molecule to its intended target. And you can think of an electrostatic interaction as kind of like two magnets with opposite poles. When you move one magnet closer to the other, you can draw that magnet in very quickly, and that's exactly what happens with an electrostatic interaction. The effect of the opposite charges is felt over a long distance, and so that effect pulls the drug molecule into its target and allows it to form other binding interactions with functional groups present in the binding site. Okay, so let's talk about hydrogen bonding. Now, hydrogen bonding is probably the most prevalent bonding mode that can be used to make a drug molecule bind to its target. So it's very important when we're looking at drug-target interactions, and therefore it's important for you to know what a hydrogen bond is and in which functional groups a hydrogen bond can form. Now, a hydrogen bond is an interaction between an electron-rich atom that contains a lone pair of electrons and an electron-deficient hydrogen atom. Now, the electron-deficient hydrogen atom is covalently bonded to an electronegative atom. Now, this induces a slight positive charge on the hydrogen. So let's have a look at that in a little more detail with the examples below. So on the left, we have a drug molecule. This contains an electronegative atom, which is shown here as an X, and bound to that is a hydrogen atom. Now, the electronegative atom is able to slightly pull the electrons that are present in the bond between itself and the hydrogen towards it. So it moves the negative charge that is in this bond slightly towards the electronegative atom. Now, this gives the electronegative atom a very slight negative charge, and it gives the hydrogen a slight positive charge. This hydrogen can then interact with an atom within the target that contains both a slight negative charge and a lone pair, such as, for example, an oxygen that contains a carbon-carbon double bond. So an oxygen that has a double bond with a carbon atom. That would have a slight negative charge and a lone pair. Now, the group that contains the hydrogen atom is called the hydrogen bond donor. So this group here, including both the X and the hydrogen, is a hydrogen bond donor. So for example, an OH group or an alcohol group can be a hydrogen bond donor. The group that contains the slight negative atom and the lone pair is called the hydrogen bond acceptor. And so this could be the carbonyl within a protein, so an oxygen that is double bonded to a carbon. Now, of course, we can have the groups the opposite way around, so the drug could contain a hydrogen bond acceptor group, and the target could contain a hydrogen bond donor. Now, the hydrogen bond donor donates the hydrogen atom to the hydrogen bond acceptor. Now, the acceptor uses its lone pair to accept the atom. So that definition of a hydrogen bond acceptor of having both a slight negative charge and a lone pair of electrons is very important. Now, some functional groups can act as both a hydrogen bond donor and hydrogen bond acceptor, and a good example of this is the alcohol group. So the alcohol group can act as a hydrogen bond donor because it contains a positively charged hydrogen, but the oxygen within the alcohol group can also act as a hydrogen bond acceptor. So the alcohol group is able to act both as a donor and as an acceptor. Now, it's very important to consider that the hydrogen bond is not just an interaction between partially charged species. It involves orbital overlap. And so what you can see here is we have a hydrogen bond donor that contains our hydrogen. Our hydrogen has a 1s orbital. Now, the hybridized orbital from the hydrogen bond acceptor needs to interact with the hydrogen. So this lone pair in this orbital needs to interact with the 1s orbital in the hydrogen. And the way that it does this, it shares the electrons in the lone pair with the hydrogen. So you end up with the hydrogen that has a covalent bond to an electronegative species and shares the lone pair that's present in the hydrogen bond acceptor. Now, because it's not just an interaction between partially charged species, because there is this, this interaction with the electrons, it means that the directionality of the hydrogen bond is really constrained. So hydrogen bonds can only be formed in specific directions. Now, the optimum angle for bond formation is 180 degrees. So you can see in this diagram up here that this is a 180 degree angle. Now, there is a bit of flexibility in this. So between 130 and 180 degrees, you can get a moderate strength hydrogen bond. And down to 90 degrees, you can still get a low strength interaction. But it's also important to note that hybridization of the lone pair orbital can also provide directional constraints. So we're not just looking at the orbital on the hydrogen, but also on the lone pair. So for example, here we have a nitrogen atom in a 6-membered ring. So we have a pyridine. Now this nitrogen atom is sp2 hybridized. Now this forces the lone pair in the nitrogen to stick out from the ring at 180 degrees. And so it means that the hydrogen bond is best formed when you have a directionality of 180 degrees to the hydrogen bond donor. So in other words, coming out from the ring, we have to go in a straight line to the hydrogen bond donor. Now, in other molecules, it might be that the lone pairs are in different directions. So for example, oxygen in water has 2 lone pairs. And so it can support it can act as a hydrogen bond donor twice. And the angle for this is around 109 degrees. So wherever the lone pairs are pointing is the direction in which we can form these hydrogen bonds. And this is really important, especially when we consider the structure of biological targets, and I'll explain why in a moment. Now this slide shows why the directionality of hydrogen bonds is really important. So here we have a molecule of DNA. Now DNA has this iconic ladder that runs up and down it, and this is formed by the bases stacking on top of each other. But it's also formed by the hydrogen bonds between the bases. So here we can see a base pair between guanine on the left and cytosine on the right. Now these have 3 hydrogen bonds that hold these bases together. One here, one in the middle, and a third one here. Now, the way in which these hydrogen bond means that the bases are flat. So they are flat with respect to each other. So even if you take them out of the DNA, they would still hydrogen bond with the same directionality. So you would have 2 flat molecules hydrogen bonding with each other. Now it's the directionality of the lone pair on this oxygen here, this nitrogen, and this oxygen that contribute towards that directionality and that hold them in the structure that they do. Now this also plays a role in protein structure, which we'll talk about later on. Hydrogen bonds can be very strong, in some instances going up to 60 kilojoules per mole in terms of energy. However, this is the exception, not the rule, and they are typically weaker than electrostatic interactions. Now, the strength of a hydrogen bond is dependent on the functional groups involved in forming that bond. And here are some examples. So for example, here we have some very strong hydrogen bond acceptors. Now the reason that they are strong is because they possess a negative charge. And the higher negative charge or the higher electron density that we have, the easier it is for a group to give its lone pair of electrons to a hydrogen atom. Now here we have some moderate acceptors. So these are all neutrally charged species, including things like alcohols, neutral carboxylic acids, so carboxylic acids in their protonated form, and amine groups. Now hydrogen bond acceptors in drugs or receptors are likely to be neutral functional groups. Now down here we have some weak hydrogen bond acceptors. So these are groups that are very poor at acting as an acceptor. So for example, sulfur, despite being below oxygen in the periodic table and possessing multiple lone pairs, is a very poor acceptor. Now the reason for this is because the electrons in its outer shell are very diffuse, and so they're less readily taken up by incoming hydrogens. Now pi systems or aromatic systems are also too diffuse to form strong interactions with an incoming hydrogen bond donor. Now halogens like to hold on to their electrons too much. They're too electronegative to donate the electrons in their lone pairs, into atoms such as fluorine or chlorine, to be a good hydrogen bond acceptor. So they're very unlikely to donate the lone pair of electrons they have to the incoming hydrogen bond donor. There are several factors that can affect the ability of a group to act as a hydrogen bond acceptor or donor. Now, delocalization of electrons can limit the ability of a functional group to act as a hydrogen bond acceptor. And so what we can see here is if we have a tertiary amine, we have a nitrogen with a lone pair, and this group can act as a good hydrogen bond acceptor. However, if we put an amine into an amide bond or peptide bond, such as that found between amino acids in proteins, we get a group that becomes a very poor hydrogen bond acceptor. Now the reason for this is that the lone pair of electrons on the nitrogen, which can be seen here, can be donated into this nitrogen-carbon bond. Now in turn this pushes the electrons from the carbon-oxygen double bond up onto the oxygen, giving you a negative charge. And this also gives a positive charge on the nitrogen. Now this means that the electrons are not available for the nitrogen to act as a hydrogen bond acceptor. But as we'll see in a moment, this process actually makes this NH group a much better hydrogen bond donor. Now as we're pushing electron density onto this oxygen, we're actually making this oxygen a much better hydrogen bond acceptor. So whilst the NH group can no longer act as an acceptor, the oxygen is able to act as a better acceptor than when there is a double bond present. Now this process, called resonance, also happens with aniline. And with aniline we get the same process, so the lone pair of electrons on this nitrogen can donate into this carbon-nitrogen bond and get delocalized into the ring, making it a very poor hydrogen bond acceptor. Now here you can see different groups that contain carbonyls and other functional groups, and you can see the effect that this has on the strength of the carbonyl as a hydrogen bond acceptor. So the best acceptor is a carbonyl in a carboxylic acid where the proton has been removed from the oxygen. And in that case, the carbonyl is the best hydrogen bond acceptor. Now, as we go back to other functional groups, it makes the ability of this carbonyl to accept lower, but it can still act as an acceptor. Now, if we look at hydrogen bond donors, a proton is a better hydrogen bond donor the more electron deficient it is. So for example, down here, we have a positive charge on this alkyl ammonium ion. Now this nitrogen containing a positive charge means that the electrons in the nitrogen-hydrogen bond are attracted much more towards the nitrogen. This means that the hydrogen can more readily act as an acceptor than if there were no charge present. Now primary and secondary amines can also act as good hydrogen bond donors. But if we put functional groups on the amine that are also electronegative, we can make the hydrogens even more readily able to act as hydrogen bond donors. Now in the next section we'll look at van der Waals interactions, dipole-dipole interactions and ion-dipole interactions. These are binding modes that are encountered perhaps less frequently, but are still important to consider when we're looking at how drugs can bind to their target.